Well, hey, it's chapter 19. Chapter 19 is really the start of this unit. Chapter 18 is kind of a starting point, but it's really small in comparison. It's got important things. Central limit theorem is important. But this is where it really starts clicking. And what's cool is, and this is what I really like, this is when statistics starts becoming the point where you sit there and say, now I see a purpose for this. Excuse me, Taco Bell. All right, this is a data set. And this is a data set that we're kind of exploring in class. And what we have here in some odd sort of data set is you have an identity here. Here is an identity for someone like an ID, like a school ID. And then you have a column of, and this is a huge, huge bunch of data here. What you have is SAT math and SAT verbal scores, and these are scores from a while ago, because I know everybody's smart now, they'll score like 500. No, I score like big time. Y'all are dumb. Well, there you are, here's a bunch of dumb people, okay? And the question that we have is, what proportion of these people scored under 1,000? Well, under 1,000 is crappy, I know. What proportion of these people scored under 1,000 combined math and verbal? Because I don't have the rating thing in here, because this is old data, and I don't care. So, I've got old data here, and what proportion of these people scored under 1,000? You're like going, well, okay, so I would just add them all up and then find out, and there's hundreds of pieces of data here. And you're like going, oh man, it's too much work. I agree, it's too much work. So instead of doing everything, which would take me forever, I could do a sample. Do a sample. What type of sample should I do? Random, you say. Random is right. I should do a random sample. Okay, so I would do a random sample. And from that random sample, I would use that to give me an estimate of the population value. What a great idea. Man, you are SMart. Okay, so here we go. Ready? You do this and you get the value of, say 14%. 14% is your answer. And I'm like, how many did you get? You go, I got 14%. And then I go, hey, Clarence, what'd you get? Clarence goes, I got 18%. Well, wait a second here. Why did you get 14% but Clarence got 18%? And you're like, because we got different samples. And yeah, so which one's right? Well, maybe neither. So what do I do? Because you have your sample and you want to make a prediction about the population off of your sample. And you're like, but this is all I've got. And maybe you don't even know Clarence or want to know Clarence for that matter. So you're like, what am I going to do with this value? Because I still have to make this prediction of the population. I'm going to sit there and say, you know what? I got 14%. But I'm willing to bet that's not exactly correct, but that's what I have. So what I'm going to do is I'm going to take it and I'm going to expand it. And which direction should I expand it? Because which way should I expand it is going to be right. Maybe my sample was right on the high side, but maybe it was right on the low side or wrong on the low side. And it's like, so which direction should I expand it? And the answer to that question is, well, probably both. I should probably take this and expand it out in each direction. Now, how do I expand? I mean, what would I use to expand this? I mean, what tools do I have in my repertoire to expand this? And you're thinking, I should, because you sit there saying, really what I want to do is I want to go out a distance in each direction. And what could I use for a distance? And wait, I got standard deviation. I could go like standard deviations. I could use standard deviations to go in each direction. And I'm like, well, that's a great idea. And because what you have here is you got, this is your value. And remember, that's your sample value, so that's your p hat, okay? And I'm like, okay, standard deviation for a proportion is the square root of p times 1 minus p over n. But I'm like going, but wait, this is what you're trying to predict. And you got this. Do you know what this is? No, because if I knew what it was, I wouldn't be doing this. All I've got is this. But I really should use standard deviation. So what am I going to use? And you're going, wait a second. I'll use the standard error. And that's the standard deviation built off of the sample value. So what I'm going to do is I'm going to go use p hat times 1 minus p hat over n. And I'll use that as my standard deviation. And I'll go out in each direction that. And I say, okay, so that's great. But how many standard deviations should I go? Because realistically, what I want to say is to myself, you know what, I want this, and I want to be pretty sure. I want to say, how many standard deviations or standard errors should I go out so that I'm pretty sure? And let's see, well, what would be a good value for standard deviation? And let's think back and well, how many would be an outlier? And it's, you know, like how many standard deviation, outlier, you know, because I don't want this to be an outlier, and I would figure that anything that wasn't here would be an outlier. And you're like, two standard deviations, two standard, like, oh, that's a great idea. Now let's think back to the 68, 95, 99.7 rule, and what percentage of the data falls within two standard deviations? You're like, 95%. And I'm like, that's great. So it's kind of like creating a normal model based here, and you're sitting there saying, if I do that, and I go two standard errors in each direction, 95% of all the data should lie in there, which is kind of like a statement going, you know what, I bet it's within that range. That's a great idea. But, here's the problem. Remember what a long time ago we said that 68, 95, 99.7 rule is really, really close, but it's really, really kind of like a lie, because it's really not 68%, and it's really not 95%, and 99.7, we said it's kind of like a rounded value. And it turns out that this 95% is not actually two standard deviations, but it's 1.96 standard deviations. That's really important, because we still want to use this 95%. 95% is a great value. I mean, that's a really good number, and it's important to us. But it's not two standard deviations, it's actually 1.96. So it should be, you know, well, I was going to say it should be the 68, 99 point blah, 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 but no. Anyhow, two standard deviations is not 95%. 1.96 standard deviations is 95%. If I go positive and negative 1.96 standard deviations from the mean, I would include 95%. So here's what we're going to do. We're going to take our value, which is p hat. We're going to take the standard error, which is p hat times 1 minus p hat over n. You know, I feel like I've been talking forever here. Is this thing even running here? Oh man, we've got a whole minute and a half left. Okay, and that's my standard error. But I don't want to go one standard error, and I don't want to go two. I want to go 1.96. So I want to go 1.96 of these, but I want to go in both directions. So what I'm going to do is I'm going to add it, and I'm going to subtract it. And what we've created is this interval that we're pretty confident that the actual population value, the actual population, which would be P, the actual population value is going to fall in that range. And that is what we're creating here. And all we need for this is your sample size and the number of successes you have, and then we can create this entirely. So let's actually do that very quickly, because we can. All right. So what? Woo! Didn't want that. All right. Let's get rid of some of this. Okay. So you said, for example, that your value was 0.14. There it is, right there. Which means that your p hat is 0.14. Let's say that you had a sample size of 20. Okay, so what we're gonna do is we're gonna create a confidence interval. We're gonna go so far to the right and so far to the left to create this buffer zone. So or we'll do it in a minute.